All right, so let's get going on this final part of today's meeting. So once again, we're going to be continuing on with our build-up to inferential statistics. And once more, it's just very helpful, I find, to remind ourselves of why we're doing this. So why are we even here in a stats course when we want to do psychology? And one of the main reasons for this is because stats and inferential statistics in particular are what make psychology possible, what gives psychology its impact. So once again, if you were dealing with autistic students and you had 14 of these students and you found a treatment that worked for these students, you developed this new wonderful treatment that increased the learning outcomes of these students. Without inferential statistics, that's all you would know, that your intervention, your treatment worked for these 14 students, and that's where the story ends, that's where the impact ends. With the skills that we're learning in this class, we will know how to intelligently generalize to the population. And that word intelligently, without bias, objectively, is very important because whether or not we generalize from these 14 students is a very difficult question for our minds, our human minds, to interpret correctly. So was this result a true result that's going to work for the entire population, in which case we should generalize? Or was this result a random chance result? Was it a fluke result? In which case we better not generalize it because we will do more harm than good promoting a useless intervention. We need to make that decision so that we can, again, objectively decide whether we should generalize or not, so we can impact the lives, not just of our 14 students, but of anybody, anywhere in the world that is an autistic child. This intervention, we could decide whether or not it would work for the population of autistic children. And again, that generalization is either the correct thing to do, yes, it will work for the population, or incorrect, no, it will not work for the population. We need to make that decision and do it objectively. And one of the things that you'll find, and you'll see this in, especially in today's society, single cases, anecdotal cases carry way too much weight in our minds. So you'll see people not vaccinating their children because they've heard of one person whose child developed autism and it just happened after the vaccine. You'll see people smoking their entire lives and not believing that it causes lung cancer because they have that one relative that smoked 2 packs a day and lived to be 97 years old. These individual or small numbers of observations, they play tricks on our mind. As a psychologist, we can't fall for that. So we need to find an objective way of taking a look at the data and saying, should I extrapolate this and apply it to the entire population? Or is it just an anomaly and it only worked for these 14? Those are the techniques that we're developing right here, right now. All right, so we're going to continue on with our look at probabilities. We're going to introduce a very fundamental concept in stats, which is known as the normal curve. And then we're going to deal with probability and the normal curve, look at how to find proportions of the normal curve that you're interested in. And then we'll take a look at the normal curve table and go back to z-scores. Z-scores are coming back, and we'll learn how to read the table, answer questions using the table, basically start to manipulate and use this normal curve to help us answer questions we might be interested in. All right, so the normal curve. The normal curve, it's a mathematical, theoretical distribution, but the key here is, the most important thing is, the reason we're studying it is because it occurs in nature over and over and over and over again. So this is the normal curve right here. It's also known as the bell curve, and many populations fall on the normal curve. Many measures in a population fall on a normal curve. So for example, height falls on a normal curve for humans. IQ falls on a normal curve for humans. So many things can be described by the normal curve in us, and we'll see why in just a moment. So this thing occurs in nature, this normal distribution, this normal curve occurs in nature over and over again because it's the outcome when many random factors combine to form a single score. And this idea of many different factors coming together to form a single score happens in nature so often, and importantly for us, happens in psychology so very often, because there's many different factors that contribute to any single score, any single ability, any single behavior that we have. So let's take a look at a visual example of many factors contributing to a single score. So this is an illustration of a normal curve in action. So what this is, it's a mechanical device. There's these little small metallic balls, and when they get flipped, they fall through this peg system. And these pegs can do one of two things. They can knock them to the left, or they can knock them to the right. So every single time these balls goes down another row, they'll hit that peg and they'll either go to the left or they'll go to the right. And then once they go one direction, they'll hit another peg and they'll go to the left or to the right. And then once they hit another peg, they'll go in those two directions as well. And what we find is that the final positions are distributed as a normal curve. So why are they distributed in this way? Well, the reason is because if you're going to end up on this side over here, that means that you have to go left every single time. So every single peg you hit, you got to go left. And when you hit the next peg, you got to go left. And when you hit the next peg, you got to go left. And when you hit the next peg, you got to go left. Basically, it's like flipping a coin and getting 7 heads in a row. That's the only way you're going to end up over here. And that is not going to happen very often. Very few balls end up over here. Why? Because in that case, you got to go to the right every single time. You got to hit a peg and go to the right. You got to hit the next peg, go to the right. You got to hit the next peg, go to the right. Got to hit the next peg, go to the right. Because of that, very few balls end up here. Most of them end up somewhere in the middle. Because the middle is where you have a combination of left and right. So you go to the right on the first one, you go to the left on the next one, you go to the left on the third, but then back to the right on the fourth. You kind of go, randomly, they're all random, but you go one way and then you go to the other way a few times, and that's why you end up in the middle. And there are way more balls that end up in that position because you can go to the left 4 times, go to the right 4 times, you'll end up in the middle. Go to the left 5 times, go to the right 3 times, you'll end up somewhere close to the middle. It just happens in nature over and over and over again as illustrated here. Now that is, those are balls coming in a mechanical device, but we as humans have a lot of our behaviors, and our behaviors, our characteristics, most often are not caused by just one thing. Psychology would be very straightforward if our behaviors were just caused by one outcome, by one characteristic. In reality, we are one of the best definitions or best examples of many factors contributing to a single score. So for example, if you take a look at SAT scores, here's the distribution of SAT scores for 2010. And you can see, lo and behold, SAT scores follow a normal distribution. The reason for that is that your score on the SATs is not just driven by one factor, right? Your scores on the SATs is not just driven by your IQ, because you might have a high IQ, but if you don't study, you're not going to do well on the SATs. It's not determined just by studying, right? If you study a lot of hours, but you study incorrectly, you're not going to do well on the SATs. Scores on SATs are actually determined by a number of different factors. Your intelligence, your study time, the involvement of your parents, your educational opportunities. Were you tutored? Did you have early success in school? Were your teachers encouraging, during your school time? All of these things come together and form SAT scores. And the people over here that are getting the massively high scores, they're the individuals where everything went in one direction. They had high IQ. They had a good educational system. They had parents that were involved. They received tutors. They had early success. They studied correctly. Everything went the right way. These students over here, everything went the wrong way, right? They have low IQ. They didn't study correctly. Their parents didn't care. Their teachers didn't care. They didn't study correctly. They had bad educational skills. Everything went wrong, and that's why they scored so low. For most students, though, they're going to score somewhere in here because some of the things are going to go right and some of the things are going to go wrong. So they have high IQ, but they have uninvolved parents. They have early success, but maybe they're not in a good educational system. So there's a number of different factors that go into forming SAT scores, and the evidence for that is that they're here on a normal distribution. You don't get a normal distribution without multiple factors contributing. And actually, I just read an article about how SAT scores are now introducing a adversity score as well to try to control for some of these other factors. So now you actually indicate what your social income is, what your mean household income is, for example, other factors that might contribute to either higher or lower scores, and you're assigned an adversity score. If you score above 50, that is indication that you suffered adversity. If you score, I believe it's above a 50 is adversity, below 50 is privilege. But they're trying to introduce those things because they understand that multiple factors contribute to these single scores. Another normal curve that has occurred, the height of males and females in the United States. So I believe this is the United States. So there's a number of different things that go into height. Height is not just determined by genetics, right? There is a genetic component, but there's also good nutrition. There's also being free from diseases, especially early on. There's proper childhood nutrition. There's very critical ages where you need to be nourished properly. There's a number of different factors that occur, and that's why, and there's a number of genetic factors that occur. It's not just one gene that determines how tall you are. It's a number of different genes. And people that are really, really tall, it's as if when they were rolling the dice on each of these factors, they rolled 6 on every single factor. 6 on genetics, 6 on diet, 6 on health, 6 on every factor that contributes to height. People that are very short, they rolled 1s on every single factor. 6 on genetics, 6 on nutrition, 6 on health, and they end up being very, very short. Same thing with males over here. So the fact that height is on a normal distribution once again indicates that there are multiple factors that contribute to this single score, this single height score that we all exhibit. And this is something that needs to be kept in mind. Yep.
Isn't it also possible to just be at an extreme end because one factor is like really, really overwhelmingly strong?
I would, if you want to.
Well, just like couldn't someone have a family that's really, really tall, and even though they don't like have great nutrition, they wind up being super tall anyway?
They would. That would contribute to their height.
Right.
They would not wind up super tall. So you can have very, very tall individuals in your family. If you're malnourished, you'll end up being the shortest in your family. Right. So you might be taller than average, but you're not going to get up to here. You're not going to get up to the super tall sections. Okay. Super tall means that everything needs to go correctly. Okay. Mm-hmm. And that's something to keep in mind when you're thinking about things on a normal curve, because sometimes you end up with very controversial data that shows up on a normal curve. And again, it's our human intuition to just jump to particular conclusions, especially if we're biased in one way. For example, if we are racist. So this is the distribution of IQ scores on, in the United States. What was the year that this was? This was 1979. So this was the distribution of IQ scores in 1979, and you can see that on average, Caucasian individuals score higher than black individuals on this IQ distribution. When people see that, they don't understand the normal curve. They don't understand multiple factors. Their minds oftentimes jump to one conclusion. And in this case, a lot of people's minds jumped to race. And they would just say things like, well, black individuals are just intellectually inferior. It has to be that one factor. They're black and we're white. They're African American, we're Caucasian. It's got to be that one factor. That's the only thing that could be causing this. And that's completely wrong. And this is one of the take-home messages of this class today. Whenever you see a normal curve, multiple things contribute to that normal curve. So the fact that black individuals were scoring lower than white individuals on IQ tests, that's just data. That does not need to be interpreted. But when you're asking why is this the case, just remember that these normal curves mean that there are multiple factors that are occurring. So it could be things like socioeconomic status. It could be things like opportunities in the educational system. It could be things like teachers' biases against particular races. It could be a number of different things that occur here. So we need to understand, especially in psychology, normal distributions, so our minds don't jump to one conclusion, the wrong conclusion, and rather we know that these curves are indicative of multiple factors contributing to a single score. All right, so hopefully that's convinced you in the importance of understanding the normal curve. So now let's take a look at how we can actually use this normal curve to make some calculations, to do some statistical work, and answer questions we might be interested in with this normal curve. So we can answer questions using this curve, such as what percent of the population scored below a 1.25. So in this case, for this normal curve here, we have a mean of 0, we got a standard deviation of 1. This is a very special normal curve. It's called the unit normal distribution curve. And using it, we can answer questions like, well, what percent of this population scored below a score of 1.25? We can identify a score of 1.25. There it is on the x-axis, there's 1.2, 1.25. And that proportion there is a proportion of people below that particular score. So if we are interested in people who, if this is people that need tutoring in mathematics, for example, what proportion of the population would benefit from tutoring in mathematics? They'll benefit if their z-score is less than 1.25 on a math test. That's the proportion of the population with a score less than 1.25. We can also answer questions such as what scores bound the middle 50% of a population. Let's say that we develop a educational procedure, a treatment that won't work for people that are doing very, very well on a particular subject, and they also won't work for people that are doing very, very poorly on a particular subject. They work more for the middle skills. Well, who's in those middle skills? How many? Well, that is the middle 50% of the population. And we can figure out the scores that bound the middle 50%, and we can know that the middle 50% will be between a score of positive 0.7 and negative 0.7. And then one last type of question that we can, or example that we can answer here, and this will be very important for all of you as you graduate and you're thinking about job placement, you're thinking about grad school placement. Sometimes you'll see criteria that you need to satisfy, especially for grad school. They might say you need to have GRE scores that are in the top 10% of all GRE scores. You need to be in the top 10%. Well, what score do you need to be in the top 10%? Well, in this case, we can identify what the top 10% of this normal distribution is, and then use the techniques we're about to see to figure out that it's a z-score, in this case, of 1.25. All right, so those are the type of things that we can do. How can we do them? Well, we're going to see that right now, but before we get to there, I want to point out the resource that we're going to be using to do these calculations, and that is the unit normal distribution curve that you have in your e-text. So if you haven't already, I highly recommend go to Canvas, go to the e-text module, open up your e-text, And then when you're in your e-text, what you're looking for is you're looking for the appendices, and you're looking for Appendix A. So this is going to be in Appendix A. It is the first distribution in Appendix A. That should show you the importance of this normal distribution. So it's the first one in Appendix A. That's where you find it. So again, if you haven't already, open up your e-text, get that appendix up and running so that you can kind of follow along with the rest of today's class. So again, that's where you find it. Go to your contents in your e-text, appendix, you're looking for Appendix A. It's the first one, the unit normal distribution. All right, so that's your table that you're looking at right there. And this is your table. This is the unit normal distribution right here. And one thing to notice first for this table, we need to learn how to read this table. It's got 3 columns. It's 6 columns to a page, but the actual table is just reproduced. It's got only 3 columns that we're looking at. The first column here is the z-score. So whatever your z-score is, you can find it in this first column. The second column here is the percent from the mean of the distribution, the center of your distribution, to your z-score. So that is the proportion of the distribution that falls between the center and whatever your z-score is. And then this column over here is the proportion of the distribution that falls from your z-score all the way to the end of the distribution. So what's above your z-score, for example, what's in the tail. And you're going to use those 3 columns to answer any questions about any proportion in this unit normal distribution curve. So let's take a look at some examples of that right now. So let's say that we have a z-score of 0.3, right? So we got our z-score right there, 0.3. We know it's above the mean, it's positive. It's 0.3 standard deviations above the mean. We learned that about z-scores. So let's say that we wanted to know what proportion of this population scored above a 0.3. Well, that blue area is the proportion of our distribution that scored 0.3 or above. So what proportion is that? Well, once we figure out the proportion that we want, all we need to do is find it in our table. So we found our z-score. Our z-score is right there, the 0.3. And then we need to make a decision, which column do we get our number from? And you make that decision by matching the area that you want up to one of these columns. So the area that we want is not from the mean to our z-score, it's not from the center to the z-score. The area that we want is from our z-score and up. It's the tail of our distribution. The tail of the distribution is the small part, the body is the big part. So this is the column that we want. We find the proportion that is listed in the same row as our z-score, and that is the percentage of people scoring 0.3 or above. 38% of our population scored 0.3 or above. We might also ask ourselves, what proportion of the population scored from the mean to 0.3? Right? So that blue area right there, what proportion of the population is between a z-score of 0 and 0.3? In this case, we once again find 0.3, but this time we're not interested in the tail. We're interested in the percentage from the mean to the z-score. So we look up the associated proportion, associated percent in that column, and we determine that 11.79% of the population is in this little blue strip right there. So far, so good? All right. So there's one last, yep.
When you mentioned that Z positive, can you go back to that point? I'm not sure, but I missed it.
Oh, that z-score right there?
Yeah, because you mentioned it's like above the mean.
Yep. So as we saw in the first hour, if you have a z-score and it's positive, that means that it's above the mean. If you have a z-score and it's negative, that means that it's below the mean when you have z-scores. And then the size of the z-score indicates how far above the mean or below the mean in standard deviations. Mm-hmm. All right, so the last kind of version of this that we can do is when you're interested in the area in the body. So let's say that we have a z-score of 0.3, and we're wondering how many people scored below a z-score of 0.3. Notice that in that case, we're interested in the body of the distribution. We're interested in the larger portion of the distribution. And in this case, we don't have anything here that corresponds to the body of the distribution. So we need to do just a little bit of logic here, just a little bit of our own deduction here. And there's a number of different ways to do this. I'll show you the way that I like to think about it. Whenever you have a distribution and you have a section that you want, you can always divide that up into two different sections. So we have 0.3. So this is 0 right here. This is a z-score of 0.3. And we want this entire area here, right? That's the entire body that we want to figure out. So notice that it's made up of two pieces. The first piece is this half right here. So this section here, this is half of the distribution because the mean splits it right in half. That's half of the distribution, or 50%. So we got this section right here. The other portion we're interested in is this little section right here. And that little section right there, that is between the mean and our z-score. That is this column right here. So whenever you're dealing with the body of the distribution, you can always split it up into 50% of the distribution. That's the bottom half in this case. And then from 0 to 0.3, that's between the mean and your z-score. And what that allows us to do is it allows us to use the table. We go to this column right here, see that we got 11.7% in this area right there. And then to that 11.7, we have to add the remaining 50%, or half of the distribution, and that gives us our final answer of 61.79% of the distribution. So 61.79% of individuals scored below 0.3. All right, so let's see that one more, another time, one more example of this. Let's say that we have a z-score of 1, and we want to know how many people scored above a z-score of 1, how many people are 1 standard deviation above our mean. That's the population. That's the tail that we're interested in. That's the area that we're interested in. We find our z-score right there. And then again, the biggest decision you need to make when you're working with the unit normal distribution table, when you're working with this table, is which column do you look in? And I highly recommend when you're doing this, draw your distribution out. Color in the area that you're interested in so that you have that visual reference, so you don't make the mistake of going, in this case, for this column. You know it's this column over here, and that blue proportion is 15.87% of your entire population. If, on the other hand, we were interested in how many people scored above the mean, but below a z-score of 1, well, above the mean, but below a z-score of 1, is that blue area right there. So once again, we need to decide which one of these columns do we look in. That area right there corresponds to this situation. That's the column you're interested in. So in this case, we go to that column, and we find out that this proportion here is 34.13%. And then finally, if we're interested in how many people scored below a z-score of 1, once again, we are now in this situation. And notice, it's the exact same situation that we had before. I don't even really need to retry. I just got to put in this new z-score here of 1. And what we have here, once again, is we have 50% from the bottom half, and then the score between 0 and a z-score of 1, that's in this column right here from the mean to z. So we find our 34.13%, and then to that we add the rest of our 50%, and we end up with 84% of your population scores below 1 standard deviation. All right, so any questions on that so far? Kind of how to maneuver or how to read the unit normal table? All right. So the last thing I want to mention is just a little bit of weirdness with the table. First off, if you have a z-score of 0, so you got a z-score of 0 right there, the proportion below that z-score is going to be 50% because the z-score of 0 cuts your unit normal distribution right in half. The proportion above is going to be a z-score is going to be 50%. Once again, because the z-score of 0 cuts it in half. And then the proportion between the mean and between your z-score is going to be 0 because your z-score is right at the mean. So there's nothing in between 0 and 0. So that's the first little bit of weirdness. The second thing to keep in mind is that your z-score and your z-score, the z-scores in your table are only positive. This is because these tables used to be printed in hardcovers on paper, and in order to keep the size of these tables manageable, what they did is they said, you know what, the unit normal distribution table, the unit normal distribution is symmetrical. It's the same on the positive side as it is on the negative side. So rather than just duplicating all this information, we're only going to have the positive side. So if you ever end up with a negative z-score, or if you need to do calculations with a negative z-score, what you want to do is draw out your distribution, draw the area that you're interested in. So if it's minus 0.3, and you draw that particular area here, and you're wondering what is that percent right there, this is equal to just flipping it and doing it with the positive numbers. So if you're ever dealing with negative numbers, draw it out, and then if it helps, just flip it, put it into a positive version of it. It's a mirror flip right here. And then you can consult the table, find 0.3, find the area in the tail, and I think what was 30, well, I can't remember, it was 12 something. We already did it, it was back there. But anyways, you can find that information. So just be aware that there are no negative z-scores listed, and the reason for that is because the table is symmetrical. All right, so let's keep going with this z-scores and the normal curve table. And right now we're going to take a look at the two major types of problems that you can do, that you can use the unit normal distribution table, the normal curve table, to calculate things. So there's the two major types of problems. You can start with a raw score and you can end up with a percentage, or you can start with a percentage and end up with a raw score. So if you're doing your SATs, you might say to a statistician, oh, I got this raw score on my SATs. What percentile rank am I in? Start with a raw score, go to a percentage. Or you might say, hey, I scored in the top 5% on the SATs. What's my raw score? Going from a percent to a raw score. Those are the two major things that we can do. So let's take a look at how to do those two things to wrap up today's class. So let's say that you're starting with a raw score. This is going to follow the steps in the book pretty much the same, except for one little additional thing that I'm going to highly recommend that you do. But I'll point that out. So first thing we want to do is we want to convert the raw score to a z-score. That's going to be a theme that we're going to see in these problems over and over and over again, because your normal distribution table is a table of z-scores. So you cannot access the table until your raw score is in z-score format. So you need to take your raw score and change it to a z-score. That is step number one. After that, this is the part you won't see in your textbook, draw your normal curve. I highly recommend draw it out. Draw the area that you're interested in, because you will be amazed at how hard it is to keep that many moving pieces in your mind and the errors that you'll make that can be avoided just by drawing out your normal curve. It takes 2 seconds. It does not need to be to scale. It doesn't gotta look pretty, but just draw it out. It'll help offload all that cognitive load from your mind onto a piece of paper so that you can do your work. So step 2, draw your normal curve. Step 3, make a rough estimate. Step 4, you look up the percentage associated with that z-score that you calculated in step 1 on the normal curve table. Step 5, you check your answer against your estimate in step 3, and that is the 5 steps. So let's put those in action with this demo problem here. So speaking of SATs, each individual section of the SAT has a mean of 50, a standard deviation of 100. Those are standardized scores. So for a mean of 50, a population mean of 50, and a standard deviation of 100, what percentile rank are you in if you scored a 333? So if you scored 333 on the SATs, what percentile rank are you in? How many people did as well or worse than you did? So how would we calculate that out? Well, we are going to follow our 5-step procedure here. First step, we convert our raw score to a z-score. So for this, we use the formula that we've been using to calculate z-scores. We take our raw score minus the mean, all of that divided by the standard deviation. We have a raw score of 333. We got a mean of 500. Do that difference, divide that by 100, and we get a z-score of minus 1.67. So notice we're dealing with a negative z-score. So this individual scored lower than the mean. That's one of the things the z-score lets us know. But importantly, we need to calculate that z-score. You cannot access the normal table without it. That's your key to get into normal table length. All right. So that was step 1. Next step, draw your normal curve. So it doesn't have to be as exact and pretty as this, right? It just needs to be there. So literally 1 1,000, 2 1,000, 3 1,000, 4 1,000, done, 5 1,000. It takes you 5 seconds to draw the curve and the area, color it in that you're interested in. Because you are, again, just beginning on this. Why make it hard for yourself and try to do this all in your head? Make sure that you're drawing out this unit normal distribution curve. It's got a mean of 0. We don't need to put that in, but just as a reminder. And there's your distribution. So draw it out so that you know what part you're looking for. We're looking for the percentile rank. We're looking for the people that scored at 1.67 and below, minus 1.67 and below. How many people scored worse than that particular z-score? So we drew it out. That's what we're interested in. Next move, we make a rough estimate. So the rough estimate, your textbook has a table or a little figure that you can use to help you make a rough estimate. There it is. There it is. There it is right there. So the one thing I'll mention about this figure, I do not know why they put positive 3 and minus 3 over here. Those are meaningless. You can get rid of those because you'll see that the divisions are only at minus 2. So don't get confused by this minus 3. Ignore it. It's not useful. I don't know why they included that. But how do you use this table to make a rough estimate? Well, what this table shows you is it shows you the percentage of the distribution between certain z-scores. So between 0 and minus 1, that's 34% of the distribution. Between minus 1 and minus 2, that's 14% of the distribution. And below minus 2, all the way to the end of the room, that's 2% of the distribution. And then you have the exact same percent symmetrical on the other side. This is there to help you sort of make a rough estimate of what range your final answer should be in. So for example, in this problem here, we got a z-score of minus 1.67. Where is that z-score on this figure here? Well, it's right about there, right? There's minus 1, there's minus 2, that's minus 1.67. So once we find out where it is approximately on this curve, we can then find the range that our answer should show up in. So for example, we know that this area here, from the arrow from this minus 1.67 and below, we know that that area is bigger than 2%, right? That's the area that's 2%. Ours is bigger. So we should have more than 2%. Our final answer should be greater than 2%, because it's 2% plus whatever this little bit is right here. We also know that our area that we're interested in is going to be less than 14 plus 2 equals 16%, because this whole section here is 16%, and we want less of it. We don't want this part, we just want that portion over there. So we use this figure here to make a rough estimate to let us know that whatever our final answer is, whatever we find, it has to be between 2% and 16%. It has to be somewhere in that range, and that's what your rough estimate will give you. It's not going to give you the exact answer, but it will let you know that when we look it up in the table, it's got to be more than 2, and it's got to be less than 14 plus 2, or 16%. All right, so we have our rough estimate. So we have that portion. So now, finally, after doing all this preparation, we are now finally ready to look up our percentage in the associated z-score on the normal curve table. So what we do for this is we have our z-score. It's right there. We find our z-score. Remember, there's only positive ones listed in the z-score table. So we find our z-score right there. And again, this is symmetrical, but we don't have to worry about that in terms of flipping it. But we now have a decision. Do we look here in this column, or do we look here in this column? And notice that we got 2 checks to make sure that we look in the right column. First off, we have our diagram. So our diagram says that we're interested in the tail. This is the column where we have the tails. So by looking at the diagram, we don't have to go through all the mental gymnastics it requires to remember what was your question 4 steps ago, what were we doing. You just need to look at your picture here and say, you know what, I'm interested in the tail. That's not the tail, that's the tail. So I'm interested in this number right here. The other thing that we have as a check is that our number has to be between 2 and 16%. That came from our rough estimate. So once again, we're in this column. We look at our answer, 4.75. That's between 2 and 16%. So that gives us confidence that we didn't make any errors. We didn't look at the wrong columm. And that is our final answer. So we check our answer against our estimate. 4.75 is our answer. That is between 2% and 16%. So we know we've done that one correctly, and we've answered that question. So in this case, if a particular individual scored 333 on their SATs, that means that they scored in the 4.75th percentile. That means that about 95% of the population scored higher than they did. That's a good indication to go back and redo your SAT. All right, so we got 15 minutes left, but I don't want to stretch this too far in case you're getting a little mentally fatigued here. So what we're going to do is this. We're going to wrap it up at this point. So we've covered the part where we're starting with a raw score and we're ending with a percentage. The next thing we're going to do is where you start with a percentage and you end up with a raw score. And that's got a 5-step procedure as well. But we're going to do that next time because it just kind of looks like we're running out of steam here. But before we get to that, before we get to like 15 minutes of practice time, I just want to mention a few things. So once again, this is chapter 4. This part about going to the unit normal distribution table, going to that normal curve table, going from a raw score to a percentage, that is all right, well, I'm not going to back out of it now. All right, that is, I lost my train of thought. This is probably why we should be wrapping it up right about here. All right, so, oh yeah, this is all exam 2 stuff. Okay, so when you're preparing for exam 1, when you're preparing for Wednesday, don't worry about what we just did with the unit normal distribution table. Don't worry about that part about looking at probabilities in the table. That's on exam 2. So use that information when you're focusing on your preparation. What I was laughing at was we have homework assignment number 6, chapter 4, part 1. Oh no, actually no, we're good on that. So homework assignment part 6, chapter 4, part 1. That's a probability assignment. That one does not involve looking up unit normal. That does not involve looking up the table. So that you are ready to go on. That is going to be due Tuesday, May 28th. Remember, we are not meeting on Monday because that is Memorial Day. The class will be, the university will be shut down. So you're ready to go on this one. But again, this is all due after the exam. So use your time wisely, prepare for the exam so that you're good to go. As always, you did your chapter 4 pretest. Make sure that you're picking up 100% on those pretests. If you don't get it, do the mastery points, earn those mastery points in the MyStatLab study plan. And next time that we show up here, we'll be having the review session at 9. We're having the exam at 10. And then we get Monday off. And then when we come back on Wednesday, we'll finish up our look at using the normal curve table by taking a look at how you can calculate things when you start with a percentage and you want to get to a raw score. Other than that, that is almost what I wanted to cover for today, but we'll wrap it up right here. So we got about 10 minutes left in class. If you're all stacked out, like I'm kind of feeling myself getting to the end of my line, feel free to call it a little bit of an early day. On the other hand, if you have any questions, if you want to start up your work on some of these assignments, I'll be around here until 12:15. Call me over and I will give you a hand. Other than that, I'm done what I wanted to cover for today.